Today we're going to do a little vector math. Vector math. And remember what a vector is. It's a mathematical quantity that describes in terms of magnitude and direction. So magnitude and direction. So for example, this arrow here is pointing in a certain direction and has a certain length. So we can say that this arrow represents a vector. It could be velocity, it could be acceleration, it could be a displacement vector, a position vector, any number of types of vectors. One way to describe this vector is in terms of polar coordinates. So the polar coordinate description of this vector might be something like, well, it's 5 units long, so this might be like 5 meters per second or something like that if it's a velocity vector. And it's inclined at an angle of, let's say, 37 degrees. Okay, so to describe this vector, we might say, okay, this is vector A. A equals 5 meters per second at 37 degrees. So vector A, and remember a little arrow over the symbol stands for vector. So this is the polar form of a vector. Okay. Another way we could describe a vector is in terms of component form. Component form. And we could take that same vector, 5 meters per second at 37 degrees, and we could break that vector up into its two components, its horizontal and vertical components. So we have that same vector there, and that's 5 long. But what are its components? Well, you might remember what a 3, 4, 5 triangle is, a Pythagorean triangle. This side would be 4, this side would be 3, when the hypotenuse is 5. So we know what the components are. So the component, the horizontal component here would be 4 units, and the vertical component would be 3 units up. So 4 units over and 3 units up. So we can describe this vector A as being a vector that has a horizontal component that's 4 units over and 3 units up. So A can be described as 4 over and 3 up. But in math and physics, instead of saying over and up, we usually use, for over, for horizontal, we use the unit vector notation of I with a little hat over it. So this would be 4 unit vectors, 4 little I unit vectors horizontally in the positive direction. And so I put a plus sign there. 3 little unit vectors up, and instead of using the word up, we'll use the letter J with a little hat over the top. So the I stands for 1 little tiny unit vector that's horizontal, and if it's a positive I, it's going to the right. If it's negative, it would be going to the left. In this case, it's positive. And then J stands for little tiny unit vectors in the Y direction. If it's positive, it would be going up. If it was negative, it would be going down. So vector A then can be said to be 4I plus 3J. So this is the component format for describing that same vector, and this is the polar format for describing that same vector. Both of them mean the same thing. Okay? This one is one we will use for the most part. However, I want you to be familiar with this format also. Okay. Another thing about vectors is that they can be added and subtracted, and visually we can draw arrows and just do them using what's called the tail to head method. Tail to head method. So let's say I have 3 vectors. We could have any number, but just to keep it simple, we'll have 3 vectors. Okay, let's say a vector that's 7 units long this way at this angle. I don't know what angle it is, but right now if we're just doing a visual inspection, it doesn't really matter. And let's say we have another vector that might be pointing straight down, that's this long. Let's say that is magnitude of 3 units, and then maybe we have one that is pointing over, let's say, to the left. That's maybe like 5 units. Okay, so we have like that, right? Now these are just absolute values that I'm writing down. How could we add these vectors? Just by using the tail to head method, or the visual method of doing it. Well, what we can do is we can start with any one of these vectors first, and it doesn't matter what order, and just watch how I do this. So I'll take this first vector here, the one that's 7 long, and I'll just draw it over into a convenient area. I'll transfer it over, maybe like right here, and I hope I'm transferring it over fairly accurately, but it's just an example. So that's the 7 unit vector there, and let's say I want to start with then the second vector I might use is maybe like, I don't care, it doesn't matter. I can use the little 3 unit vector, so I'll bring that down here, slide it down. Vectors have the property where you can just slide them as long as you keep their angles the same and their magnitude the same. You can just slide them around. I'm going to touch the tail of that second vector to the head of the previous one, making sure that I keep the same scale that I had earlier. And you can see I'm just eyeballing it, just visual. I'm not making any measurements or anything like that. Now I take that last vector there, and I'll slide it down so the tail of it right here touches the head of the previous one. So here we go. Okay, and so we have right there. So that's the vector that's 5 long. Okay, so I started out with one vector, and then another vector, another one. I touch the tail of the next vector to the head of the previous one, and you keep doing that until you run out of your vectors. And then to get the sum of those vectors, if you want to add them up, basically I just draw a little arrow from where I started, which is right here. This is where I started, to where I finished. I finished here. I'll just draw a little arrow. The light went out again. It's a pleasant little system that we have. Okay, and I'll just draw that arrow there. There. That purple arrow right here is the sum, or the resultant of those 3 vectors added up. So this is the resultant vector right there, that purple one. And if we used a ruler and a scale and so forth, we could figure out what the length of that vector is relative to those other ones. We could figure out the angle too if we used a protractor. Okay? So this is the resultant vector. That's how you add vectors using what's called the tail to head method. It's just a graphical or visual way of adding vectors. Okay? Now, that's all well and good, but sometimes it's better to actually do trigonometry to figure it out. Okay, and so we're going to do that next time.